Okay, let's go to the next topic, magnetic field, magnetic forces and magnetic fields. Let's just start with a magnet. Imagine this is a magnet. A magnet has a north and south pole. So we know that like poles repel, and unlike poles attract. Correct, attract. Now let's try to find the magnetic fields around this magnet. This is a magnet. Okay, to do that we need a test magnet. In the same way as we used, right, or we found the electric field for charges using the test charge. For charges, remember the test charge is the positive charge. Right here, the test magnet is gonna be a compass, right? So we have test magnet and it's gonna be a compass. Remember, so the compass in this direction, and this right there indicates the north, seeking pole, right? And now we apply these laws, right, to this magnet. What happens when we place a compass right here? Well, the north pole is attracted by the south pole. So we have this direction. What happens right here? It's gonna be repel, right? What happens right here is gonna be in this direction, correct? In this way, right, and so on. Now let's connect all the points. When we connect all the points, what do we have? We have the magnetic lines in this direction. We can do it also right here. We repeat it, right, and so on. Also on the other side, right? This is one magnetic line, another magnetic line, right, and so on. And this is the magnetic field. The symbol for the magnetic field is B. It's a vector, means has magnitude and direction. Okay, for example, we can see right here that the direction of the magnetic field is from north to south, right? According to the compass, according to the test magnet, correct? It goes from north to south, right? And at each point, for example, this is gonna be the magnetic field. Right here, it's gonna be the magnetic field. This tangent to this magnetic line, correct? And so on, right? And so on, right here, tangent. That's the magnetic field. Let's apply these ideas to the Earth, for example. Imagine this is the Earth right here. This is the equator, this is the North Pole, South Pole. Let's place a compass right here. What happens? Being attracted, right? If these two attract mean if this is north, this is gonna be south, correct? So means that, or this is south, this is north, it's gonna be south, right? Like over here, this is north, it's gonna be attracted by south. So this is north, it's attracted by south, not by north, right? By a south, right? Means what? Means that the Earth simulates having a huge magnet inside with the south pole, south magnetic poles by the north geographic pole, correct? In this way. And of course we have the Earth magnetic field, correct? In this way. You see it? Perfect. Now we already described the field. Let's go to the forces. Let's try to find the forces acting when we are dealing with a magnetic field. Okay, let's do it. Let's compare again the magnetic field to the gravitational field or electric field. For simplicity, let's use a constant magnetic field. Remember how we use the gravitational field? Well, we found that by the ground, correct? We have the G is constant, the gravitational field. Also, we use the same constant field, right, for charges, correct? You might have a charge right here, positive, negatives, these are plates. So we found that also we can create a constant electric field. Remember, we do this because it's easier to find some quantities related to the field when this is constant, right? let's do the same thing for the magnetic field. Let's create a constant magnetic field. To do that, we create a huge magnet, right? And this is north and this is south. And we know that the magnetic field goes from north to south, correct? And this is the magnetic field. Now, let's use charges in this case. What happens if we have a positive charge, right, or test charge? If the charge is at rest and we place it inside, right, at rest, well, nothing happens. It has only what? This charge has only a electric field. But what happens? We mentioned that according to the law of the poles, correct? Like poles are repelled and like poles attract. So we have interaction only when we have a magnetic field. Magnetic fields interact with magnetic fields, and electric fields so far interact with magnetic field, electric fields, correct? Okay, now but it's found by the experiment that if this particle, positive charge, such charges, are moving inside of this constant magnetic field, correct? A force is present right on the charge. This charge is being affected. Now it's changed direction, right? Because a force is present. And that force is found, again by the experiment, is proportional to the velocity or the speed. Correct? Means what? If we increase the speed, we increase the force acting on this particle. Also it's found that if this particle moves parallel or anti-parallel to the magnetic field, nothing happens. There is no force present. But when it moves perpendicular to the magnetic field, the force is the maximum. Now, it means that the force also depends on the direction. If the direction is parallel or anti-parallel to the magnetic field, the force is zero, minimum. If the force is perpendicular, the force is maximum. Now, which function from trigonometry help us to relate this property? Okay, we have, remember, sine, cosine, or tangent. Well, again, when it's parallel, when angle is zero, right, the magnitude is zero. When it's perpendicular, the magnitude is maximum. So the function is sine, right, sine theta. So sine theta, when the angle is zero, sine is zero. When the angle is 90 degrees perpendicular, is the maximum 1. Okay, so also this force is proportional to sine of the angle theta. Correct? Also it's found that if we increase the charge, the magnitude of the charge, correct, also the force increases. Correct? So force is proportional to the charge, is proportional to the angle, it's also proportional to the speed. But this is the case when we have this magnetic field. What happens if we increase the magnetic field too? If we increase the magnetic field, also the force acting on the charge increases too. Correct? Okay, in this case, then we can say that the force acting on the charged particle is proportional to B, right? The strength of the magnetic field. Now let's combine these two. These four factors. Remember, these are factors for this force, the magnetic force. So what do we have then? Force is proportional then to the charge. What else? V B sine theta. Okay, let's eliminate this symbol. How using a constant? So the force is equals to a constant charge V B sine theta. It's found because we can take this as the unit for the magnetic force. If we take this to be the unit of the magnetic force, we take then K, the constant of proportionality equals to 1. And then what do we have? This is the magnitude. This is the magnitude for the magnetic force. It's equals to the charge times the speed times the magnetic field times sine theta. Correct? Perfect. This is the magnitude. What should be the direction? Look, the direction of the force is given by the right hand rule. So these fingers represent the magnetic field, this thumb represents the speed, and the quantity perpendicular to this plane, because we have a plane, this form a plane, right? My palm is a plane, and the quantity perpendicular to that plane is gonna be the force. So the force is perpendicular to the magnetic field, to the speed, right? To that plane, and that's gonna be the force. All the time it's perpendicular in this way, correct? Perfect. And of course, we have a new quantity, right? The magnetic field. The magnetic field has a unit. The unit of the magnetic field unit gonna be Tesla. Maybe you have a Tesla at home, right? Okay, Tesla, the symbol is T. Also, we have another unit, Gauss. Correct, G. And these are related in this way, these two units. 1 Tesla is equals to 10 to the 4 Gauss. Correct, this is again the unit for the magnetic field. Perfect. Now, because the magnetic field is perpendicular to the velocity, and to the magnetic field, is easier to illustrate the behavior, right, of the force, to use this convention. Imagine that we have an arrow, right? This is the arrow right here. Imagine. So we have, this is the tail, this is the tip, right? And that's the tail. Imagine. When we're seeing, right, when you're over here and you see arrows coming toward you, you will see, right, this dot right here. This is the magnetic field coming toward you. And you over here behind, and the arrows goes in that direction, you will see the tail, right? The tail. Like that. And also this is the magnetic field. But this is the magnetic field coming out from the page, correct? And these are going into the page, let's say, onto the wall. Or into magnetic field, into, let's say, wall or page. You have a book, right? And this is a magnetic field coming out, right, from page, right? Or from a wall, the wall. Or it's coming out, going into the this out of page, or out of wall. This is into wall, right, or into the page. Sorry. This helps us again to study better these forces and fields. Okay, perfect. For example, imagine that we have a magnetic field, right, coming out, right, of the page, and we have a particle, right, moving in this direction with some velocity. Now, what should be the path? We can find the magnitude, right? This is the magnitude of the force. Correct, but what should be the direction? Well, we use the right-hand rule. What is the direction then for this field? The magnetic field is coming out, right? Perfect, and this is the velocity. So what should be the force? Downward. So it's found that in this case, this is the path of the charge. Correct. What about do we have this field? This magnetic field, imagine. Oops. For simplicity, we're going to be constant. Remember, we take it constant. And the same thing. This is the charge right here. It moves with some velocity. Okay, we use the right-hand rule. What is the direction of this field? Right into the page. This is the velocity. What is the force? Right, perpendicular. It's gonna, in this case, gonna be upward. Correct. Perfect. what is the difference between these two? Well, it's just the direction. Also, look, when we're dealing with magnetic field, right? The velocity is constant. If the velocity is constant, the path of the particle, charged particle in this case, is gonna be circular path at constant speed, right? Circular path at constant speed. Correct? Perfect. For example, look, imagine one more time. Imagine that we have gravity. Let's compare these three fields. This is gravity, right? This is G. Imagine that this is a mass and we have this velocity. What should be the path of this mass? Parabola, correct? What about if we have an electric field? Constant. Remember, this is constant magnetic fields, constant electric, constant magnetic. Okay, let's see how they looks like. Okay, this is positive, right, and this is negative. The same thing. How is the field? Well, in this direction. This is the electric field. Imagine one more time we have a positive charge moving with that velocity. What do we have? Well, the same path as this one. It's a parabola. Correct? What happens if we have a magnetic field? This is, let's say, south, this is north. Imagine. Okay, let's do it. It's gonna be again constant, okay, constant magnetic field. If we have a charged particle right here, what happens with some velocity? We're gonna be create right a circular path, correct? It create a circular path. It's gonna be moving right in this plane. This one goes down, right? This one goes right in circular path, what produces a circle, for example. That's correct? Yeah, it goes magnetic field, velocity. Actually, the circle goes in this way, right? Actually, the circular path should be one more time. It's a magnetic field, goes down, velocity. So it's gonna be perpendicular. It's gonna be correct in that way. Imagine that's gonna be horizontal circle, right? Horizontal circle, right like this, right like that, in one plane, perpendicular, and the speed is constant. Right here, the speed increases, right? We know that what happens to forces acting when we have gravity, right? Right here, forces acting, we have the electric field, and this is the gravitational field. What about in this case? In this case, the force acting is perpendicular to the path. Right here is not perpendicular to the path, it goes with some angle. When it's perpendicular to the path, for this case, right, it's gonna be always toward the center of curvature. Correct? And produces, remember we call that centripetal force, remember? So it's gonna be centripetal force and produces a circular path. This is a circular path. This is parabola. See the difference? Okay, perfect. Now, we can have cases where the particle is not moving in circular path when it is inside of a magnetic field. It happens when we combine these two fields. Let's do it in this way. For example, imagine that we have this this plate, correct? And we have an electric, it's positive, negative, and negative, correct? And this is the electric field, correct? The electric field is constant. What happens if we have a positive charge going inside of this magnetic field? Well, the path is gonna be right toward the negative plate. But we want this to be moving right in a straight line. How we can make it? Well, we introduce this into a constant magnetic field. Now this is a magnetic field. Okay, magnetic field is constant. what happens in this case? Look, when we have only electric field, this is the path. If we have only magnetic field, right, that should be the path. How we can create this to be straight line? Well, when the force produced by the electric field is equals to the force produced by the magnetic field. And what is this force? This force equals to charge times the electric field. And what should be this one? This is equals to, it's right here, right? Charge V, B, right, sine theta. But what is the angle between the magnetic field and the velocity, right, in the magnetic field? Correct? Between these two, it's gonna be 90 degrees. So sine 90 is equals to 1. So this quantity is equals to 1. Correct? Perfect. As you can see, charge is cancelled, and what do we have? V is equals to the electric field over the magnetic field. Right? Using this condition, we can create, right, the particles to be moving in a straight line. This is very important. This helps us to find the speed of light. This equation later in the next chapters. Okay, great. One more time, imagine that this is the magnetic field, right, into the page. And at the beginning, this is a positive charge. And we give some speed at the beginning, right, one impulse, correct? What happens? Well, it's gonna be moving, right, in circular path, imagine. We have more, right, magnetic field. So it goes in circular path, so it has a radius, right, R. And speed is constant. And we have the centripetal force acting, right? We have a centripetal force. Now, imagine that we're looking for the radius for this circular path. How we can find it? Well, we know that every time we have a particle moving in circular path at constant speed, the net force is equal to the centripetal force. So we have that the net force is equal to the centripetal force, right? But using Newton's second law, remember, the net force is equal to the sum of all the forces F1 plus F2, correct, plus and so on, must be equals to, in this case, the centripetal force. Right, but how many forces are acting? Only one, right? Only one force. What is that force? The magnetic force. Then the magnetic force must be equal to the centripetal force, correct? So how do we have? The magnetic force must be equal to the centripetal force. And what is the magnetic force? Well, it's gonna be this one. Charge times V, B, sine theta must be equals to M, B squared divided by R. Correct? Sine, one more time, V and B are perpendicular, right? V and B are perpendicular, so sine theta is, or sine 90 in this case, is 1. Perfect. And then what do we have? Well, we have that the charge times V, what else? B is equals to, also look at this cancel with this, and what do we have? We have, remember, we're looking for R, we're solving for R, right? Let's use cross multiply, and what do we have? R, the radius, is equals to M, mass of the particles times the speed divided by charge, times B, correct? And that's the formula that give us the radius, a curvature. Radius equals to mv charge. Remember, when we're dealing with charge, we use magnitude so far, magnitudes to avoid, right, negative radius and so on. So we use the magnitude right here times B, also magnitude. Okay, perfect. So it's gonna be the radius. So we found again that this is gonna be the path of a particle when the direction of velocity is perpendicular to the magnetic field. Now what happens if there is an angle? When we have an angle, correct? Imagine that this is again the magnetic field, and now the particle moves with this angle v, with this velocity v at this angle theta. In that case, right, what do we have? Well, in that case, we have a helical motion. This this velocity has component, right? One, let's say in the x direction, and one in the y direction. And what do we have? Well, we have this helical motion, right? Helical motion. Okay, perfect. Great. Now let's go to the next topic. Imagine that instead of charges we have a current, we have a wire. Let's do it. In this case, right, one more time, this is the constant, right, magnetic field, and now this is a wire, right? This is magnetic field, so the direction is constant, and this is we have current inside, right, of this wire, correct? The length of the wire, right, is L. Now, how we can find the force acting on the wire? Remember, the wire is, now it has a current. The current is formed by charges. Now we have charges moving right inside of the wire, right? Charges, right? So we have a then magnetic field, because they're moving. That magnetic field of the charges interact with the external magnetic field. Perfect. Now, how we can find then this net force? The net force acting on the wire is equal to the sum, right, of these forces, individual forces, correct? Q sub I, right, B sub I, B, they have the same speed, B times sine theta, correct? Perfect. And then what do we have? Well, in this case, this is equal to the sum of these charges. What should be V? V is distance. I mean, speed is distance divided by the time. We can take this divided by the time right here. Distance, the distance is called L, right? V sine theta. What is this? Charge divided by the time. Charge by the total charge divided by the time, remember, is current. That's current. Current, remember, current we found last time. Charge divided by time. The total charge. So this is equals then to current times L magnetic field sine theta. And then this should be, right, the net force acting on the wire. Perfect. So this is for the wire is equals to current by length of the segment, in this case, magnitude, the strength of the magnetic field times sine theta. Correct. Perfect. We mentioned one more time that a charge moving, right, produces the magnetic field. Imagine that we have this positive charge moving in this direction, x direction. This is V, this is charge, right? The field at the beginning has only electric field, but the electric field covers some distance. Imagine it goes right here, the electric field. Okay, at this point the electric field is changing. Every time we have a changing electric field, produces or induces a magnetic field. So right here we have a magnetic field. Also at this point, right, we have magnetic field. The same thing happens in this direction. We have that also at this point. The electric field produced by this charge is changing when this particle moves to the right. So also we have right here a magnetic field. Also right here, right? Right here we have the magnetic field right in this way. In this way how the magnetic field is created. When we change the electric field, and in this case, right, we can say, right, this is the angle theta. The angle theta created right here. Now, what happens if we have a wire? The same thing, when we have a wire, right, for each point right of the wire, we have the magnetic field. The magnetic field is coming in circles, right? Circular loops, make loops, circular loops, like in this case. It's not like the electric field, right? The electric field starts at positive charge and end at the negative charge. For this one, it's continuous, right? Continuous loops. Correct. And what should be the direction in this way? Imagine that this is the current one more time. So we use the right-hand rule, right? In this case, the thumb represents the current, right? And when we bend, we curl the fingers represent the direction of the magnetic field, right? In this way. It is current, and this way is the direction of the magnetic field, correct? This is the magnetic field. And it goes, in this case, it goes counterclockwise, right? Counterclockwise. When you see from above, right? That's the direction of the magnetic field. In that way. Okay, perfect. Now let's try to find another equation that helps us to relate the current and the distance. Okay, let's do it. Let's do it. Imagine that we have the current in this direction, and we're looking for the magnetic field at this point. Distance, let's say r from the or distance d. Here's distance d or distance d from this wire. What happens? Well, if we increase the current, correct, the magnetic field increases at this point, correct? So the magnetic field is proportional to the current, correct? If we fix this point, if we change the current, correct, at this point, the magnetic field increases if we increase the current. Now let's do the opposite. The current is fixed and we change the distance, right? We increase the distance from this wire. What happens to the magnetic field? Well, if we increase the distance from the wire, the magnetic field increases if we keep constant the current. So we say then that the magnetic field is inversely proportional to the distance. If we increase the distance, the magnetic field decreases, correct? Now let's combine these quantities. Look, what do we have? We have the magnetic field is proportional to the current divided by the distance. Okay, let's eliminate the symbol. Remember, we use a constant. So in this case, the magnetic field is equal to a constant. Let's call it K prime times what? Times the current divided by D. Okay, now because the magnetic field is coming in circles, right? It's coming in circles, concentric circles, correct? This is the wire right here. We can use, because right here we have the distance. The distance is gonna be like the radius right here, right? Radius or distance, the same idea, correct? Also we can use, radius to match this notation right here, the radius, correct? But what should be the formula for circumference? It's easier in this case. It's equals to what? 2 pi r. Correct? Now, let's go back to this equation. It said B, magnetic field is equals to this constant K prime times the current divided by r. Okay, perfect. Now, because I want to create circle, right? Circumference, right? Loops in circular shape. Correct. It's better to use this quantity, right? We already have radius. What happens if I multiply by 2 pi and divide by 2 pi? Well, the equation is the same, correct? Now, let's make this quantity mu k equals to 2 pi times k prime, right? This is gonna be mu sub naught, the symbol, type letter called mu, mu naught. Okay, when we do that, what should be the magnetic field? Equals to, is equals to mu naught times current divided by 2 pi r. Correct? And this is the formula that is used for this case. Correct? It's going to be magnetic field intensity is equals to mu naught current divided by 2 pi r. In this case, mu naught is equals to is a quantity. Correct? I'm looking for the value for mu naught is a quantity equals to mu naught is equals to 4 pi is equals to 4 pi times 10 to the negative 7 Tesla's meters per amp. Right, Tesla's meters per amps. That's gonna be the unit for mu naught. Okay, perfect. Wait, I'm looking now. Let me see that unit. Okay, that's correct. That's the unit for the for Tesla. Also, look, Tesla. We mentioned that is the unit for the magnetic field. What's coming from here? Let's start for B. B is equals to what? It's equals to force divided by the charge times V. Okay, what is the unit for force? The unit for force is Newton. The unit for charge is Coulomb, right? And the unit for speed is gonna be meters per second, correct? But this is also arranged in this way. This is Newtons, coulombs per second, correct, times meter. What is coulomb per second? Coulomb per second is the unit for current. Right, current is coulomb per second. So in this case, B, and what should be the unit for B? Tesla. Right. So 1 Tesla then is equals to what? Tesla is equals to Newtons, what else? Amps per meter. Right? Perfect. That should be again the unit for Tesla. Right? Newtons, amps per meter. Okay, great. And with this, we finish this part of this chapter, magnetic forces and magnetic field. And let's finish this in the second part. Okay. Thank you and see you in the next video.